October, November 2023. Paper 2, Very Much. Question 1. Table 1.1 shows some properties of elements of the phosphorus, sulfur and chlorine. And the first ionization energy of sulfur is not shown. For this part A1, complete table 1.1 to show the numbers of electrons in the 3p subshell and the total numbers of unpaired electrons in these three elements. Okay, first, refer to this orbital diagram. For phosphorus, the numbers of electrons in 3p is here. So there are 3 electrons there. And these 3 electrons, they also unpaired electron. So therefore, in this table 1.1, for the phosphorus, there are 3 electrons in the 3p subshell and 3 unpaired electrons. For sulfur, there are 4 electrons in 3p orbital and just 2 unpaired electrons here. So it's 4, 2. For the chlorine, in this 3p subshell, it has 5 electrons. And the total unpaired electron is just 1. So therefore it's 5, 1. Part 2. Construct an equation to represent the first ionization energy of phosphorus. Always start with gaseous atom. Must be 1 mole of gaseous atom. This is a definition. 1 mole of gaseous atom, it will release 1 mole of electrons to form 1 mole of gaseous ion. And you must put the state symbol, must put gaseous state. So this is the how you construct and how you give the equation. It's easy. Part 3. 3 possible values for the first ionization energy of sulfur are given. 1000, 1160, 1320 kilojoule per mole. And we should choose the one that lower than the phosphorus. So for this phosphorus is 1060, we should choose the one that lower than phosphorus. Why? Because if you compare the electrons in the phosphorus and sulfur, then we'll know. For the phosphorus, there are 3 unpaired electrons in 3p, and for the sulfur, there are 4 electrons. But in these 4 electrons, what we can see is there are 1 pair of electrons here. So, and this pair of electrons, because they are both electrons and negative charge, they have a repulsion. Since they have repulsion, then the electrons in this orbital easier to remove. When it's easier to remove, of course, it need to use lesser energy. So therefore, the sulfur is going to use lesser energy compared to phosphorus to release this electron, the first electron. So the first IE for sulfur is lower than the phosphorus because of this spin pair repulsion effects. And in part 3, we just have one choice, which is 1000. Because phosphorus is 1060 and 1000 is lower than 1060, so we choose this. And you need to explain your choice by comparing your chosen value to those P and the chlorine. Means you need to explain and compare sulfur with the chlorine and the phosphorus. That's what they need. If let's say we want to discuss about the chlorine, chlorine in the table has 1260 kilojoule per mole. So it has highest first IE. What is the reason? So you just explain like this. Chlorine has the highest first IE because it has the most nuclear charge to the, nuclear attraction to the outer electrons than this sulfur and phosphorus. So why? Why it has the most or greatest nuclear attraction among these three? Because the chlorine has the greater or greatest nuclear charge among these three. So this is explanation for the highest first IE of the chlorine among these three, because of the greater nuclear charge. For the sulfur, we know that sulfur has the greater nuclear charge than phosphorus. This is true because sulfur is on left hand side, and it has more proton number. Even though sulfur has greater nuclear charge, but the sulfur has 2 electrons in the p orbital, which resulting the spin pair repulsion that I told you just now. And this spin pair repulsion will let the electrons release easier, and therefore it needs lesser energy. So that's what you need to explain. For B, so we have now 3 anion, the phosphite, sulfite, and chloride. And these 3, they are in the same period, and phosphorus gains 3 electrons to form this phosphite, sulfur gains 2 electrons to form sulfite, chlorine gains 1 electron to form this chloride. And now they have the same electron configuration, but proton number difference. We know that the chloride has the greatest proton number among these 3. So what we expect is the chloride is going to have a greater attraction, and the size must be smaller. Because now the electrons number same, the shielding effect is actually the same. Same shielding effect, but proton number is higher. Okay, attraction is greater, size confirmed smaller. Part 1. Give the full electron configuration of this phosphite. Initially, the sulfur is 1s2, 2s2, 2p6, 3s2, 3p3. And the p3 now gains 3 electrons, because 3 negative here. Gains 3 electrons, now become 3p6. So this is the argon electron configuration. Part 2. State the trend in the ionic radius shown by the phosphite, sulfite, and chloride. So this is a trend that I told you just now, means across the period. So the size or ionic size smaller. Okay, what is the reason? Ionic radius decreases from this phosphite to chloride. It because the increased nuclear charge, attraction is greater, and the attraction is greater means because of what? Because of nuclear charge increases and same shielding effect. Because they're having the same electron configuration now, therefore the attraction is greater. Attractions to the outer electrons increases from the phosphite to chloride. This is what you need to explain. For part C, we have the 3 separate samples of the sodium chloride solution and 3 tests for these solutions. And you need to give observation. It's better to show you this. Okay, the first test is to add bromine to the sodium chloride solution. Bromine is brown color. When this solution add to the sodium chloride, if no reaction, then the whole solution would turn brown. This is normal. Okay, what we are going to see is no change, means no reaction, means bromine brown color added to colorless, the solutions turn brown. is actually no reactions there, so no change. Why no change? Because we know that bromine is a weaker oxidizing agent, so it's not really able to oxidize chloride to chlorine. If let's say now we try to push the fluorine gas into this sodium chloride solution, then the fluorine will try to oxidize the chloride. Bromine cannot, because bromine is a weaker oxidizing agent. So we see nothing, means no change, no reactions there. For the second test, add a few drops of the concentrated H2SO4 to the sodium chloride solution. This part, many candidates will give the white fumes. But you have to understand, the few drops of concentrated H2SO4 is not added to a solid, it's added to a solution. When the concentrated H2SO4 added to a solution, it will not have that effect, means it will not really react with these sodium chloride and form the white fumes. So no white fume will be formed. It's only applied for solid, remember. When a concentrated sulfuric acid added to this sodium chloride or these sodium halides, so it must be solid, then it can really react, means that it can really react. Whether there is a redox reaction or not, then there is another steps. Okay, so for this one, remember, no visible reaction. For this one, no white fumes, because the strong and concentrated H2SO4 added to a sodium chloride solution. If it's added to solid, yes, you see the white fume. For the last test, addition of a few drops of the silver nitrate. This one is very easy. Silver nitrate solution is a clear solution added to sodium chloride. We know that the silver ions will try to form a precipitate with chloride. Okay, so the precipitate is silver chloride, white precipitate. So white precipitate is formed. Okay, these three observations. Part D. Now we have POCl3 and PCl5. But this question is mostly about POCl3. So it's mentioned it has similar chemical properties to the PCl5. And these two statements is very important because it's telling us the structure is a simple molecular. POCl3 has a melting point of 1 and boiling point of 106 degrees C. This one is actually quite low. I mean, the melting point and boiling point is quite low. It's showing that this POCl3 has the simple molecular structure. For the giant structure, we know that it's going to be very high melting point and boiling point. It's 1,000 and above sometime. And second, POCl3 reacts vigorously with water, forming misty fume and acidic solution. This one also telling us is the molecular, simple molecular structure. Because for giant structure like diamond graphite, SiO2, they will not really easily react with water and form something. So these two observations or these two statements is telling us that this POCl3, it must has the simple molecular structure. Okay, if you understand this, then you can, of course, explain nicely. Okay, part 1. Explain how the information in D suggests the structure and bonding of PCl3 is simple covalent. Okay, simple covalent means it's a simple molecular structure. So for this one, POCl3, because of POCl3 has relatively low melting point and boiling point, which indicates it has a weak van der Waals force between the molecules. Means it's just a simple molecule, means this is one molecule, this is one molecule. It has no network, no covalent network. It's just like this. Between the molecules, it has a van der Waals force. And this van der Waals force is easy to break. That's why it has a low melting point and boiling point. This is the first one. And of course, the second statement is telling us the POCl3 is actually undergo hydrolysis. Whenever it reacts with water, so it will undergoes hydrolysis. So these are the two statements you need to give. And part 2, suggest or construct an equations for the reactions of POCl3 with water. Okay, since it's just now I told you that it's very similar to PCl5, then it should form these two, H3PO4 and HCl. You just put these two products and then you just balance it. It's just similar to the PCl5. Okay, this one you should know lah. Now, part 3. POCl3, now you need to draw the dot cross structure. The first thing that you need to do is you must know how many valence electrons of the elements involved. Phosphorus is group 15. It has 5 valence electron. Oxygen is group 16, 6 valence electron. Chlorine's group 17, so it's 7 electron. And chlorine has 3 atoms there, so times 3. So total is 21 here. 21 plus 6 plus 5. In your dot cross structure, you must make sure total 32 electrons in there. And in this dot cross structure, you need to make sure the phosphorus will share 2 electrons with oxygen from the 2 bondings, from the double bond. And the phosphorus will share 1 electron to the chlorine, to this 3 chlorine, means 3 electrons involved, means total 5 electrons from phosphorus used up, okay, to form the bonding. And the phosphorus actually, this electron is not really a chief octet. The rest is a chief octet. For the phosphorus, this configuration we call expanded octet. Means it's more than that. Why and how, you'll not really need to know. For E, part E, now we have this equation. PCl3 reacts with oxygen, form POCl3. And the table, first you need to know the structure, how the structure looks like. PCl3 in there, it has 3 PCl bond. Remember this, 3 PCl bond. Oxygen OO double bond. In the POCl3, it has 1 PO double bond, 3 PCl bonding. Because later when you try to calculate the enthalpy or bond energy, so you need to use all this. And in this table 1.3, the formations of PCl3 and POCl3 is given, and this one is the bond breakings of the oxygen, means the bond energies. So it's 496. We will discuss this one later. Let's move on to the part 1, the definition. Okay, define enthalpy change of formation. So always remember, its formation is to form 1 mole. 1 mole of the compound. This is the first key you need to give. So enthalpy change when 1 mole of the compound form. And this compound must form from its constituent elements. Means, let's say for this example, if we want to form the PCl3, so we need to use phosphorus and the chlorine. So these are the elements that used to form this. And these elements, they must in their standard state. Means phosphorus must be a solid, chlorine must be a gas. Under standard condition. Standard condition is 101 kilopascal and 298 Kelvin. So part 2. Part 2, this is a calculation, and you need to use the enthalpies that given in this table 1.3. And you need to calculate the bond energy of PO double bond. First, it's better for you to construct the hash cycle. Start with, I teach you the method. Always refer to this equation. This is the reactions and is the delta HR, the reactions that we need to deal with. And we start with this equation and we put the elements down there to link this reactant and products together. We must put phosphorus, chlorine, and oxygen, because these are the elements used to form the reactants and the products. And we need to use the enthalpies that given. Formations of PCl3 negative 289 kilojoule per mole, and formation of POCl3 negative 592. So substitute to this hash cycle. Because it's formed 2 moles, so we need to times 2. 2 times negative 289. And this one is 2 times negative 592. After that, we try to find the delta HR first. So delta HR plus this enthalpy equal to this enthalpy. So we have this relation. After you calculate, you get the delta HR, this one is negative 606. Then when you get this one, then you can get the bond energies of the PO double bond. Okay, remember, when you try to use bond energy, you must use the bond energies, the sum of the bond energies of reactants minus the sum of bond energies of products. Reactant, they are this one, PCl3 and O2. Product is this, POCl3. Why is negative? Because the negative sign is the formation, means when the products form, it has a bond formation. This negative sign is represent the formation of the bond of the products. Because the reactant, we need to supply the energies to break the bond, so it's endo, so it's positive here. Okay, and product is formations of bonding, so energy release, so this one is negative. Now, from the structure, we know that I told you just now, in the PCl3, it has 3 bonding, 3 PCl bonding here, 3 PCl, and we have 2 molecules, so total 6 bonding. PCl bonding is 6 bonding. Okay, therefore here is 6 times the bond energies of PCl plus 496. This one is the oxygen. So we need to break this oxygen, OO double bond. So plus 496. Okay, minus this one. So 2 times of the PO double bond and 6 times of the PCl bond because of this. Because in one molecule, it has 1 PO double bond and 3 PCl bond, and the product also 2 moles. So need to times 2. Therefore, now it becomes 2 and 6 here. After you're able to do this part, so we know that the PCl actually you no need to find it, just cut it. So now what's remain? Negative 606, the delta HR, equal to 496 minus 2, okay, times bond energies of PO double bond. Okay, so rearrange, then you get positive 551 kilojoule per mole. Okay, that's all. Thank you.